Thank you everyone for coming to the ITC lunch. We just had a very interesting colloquium, ITC colloquium by Jim Stone. Where is he? Oh, over there. And he will speak a little bit later. I should say that, well, first, Jim, other than doing pioneering numerical work, as of recently was selected to be the next chair of the astronomy Department of Astrophysical Sciences at Princeton. So he replaces David Sperger, that was in that position for a while, and David started in the Center for Computational Astrophysics in New York City, and Jim is taking his position. I wanted to congratulate him, but also Princeton for making such an excellent choice for the next chair. I'm sure Jim will do a fabulous job. Actually, I will not mention names, but a chair of another department approached me, and a newly selected chair, and I gave him my condolences. He said, "Yes, well, you must be familiar." I said, "No, it really depends on the department." And in my case, it's a pleasure actually to work in our department. But anyway, I think in your case, it's also a pleasure. It looks like every week there is something interesting to mention just at the opening of our lunch. And as many of you remember, last week there was a Nature paper claiming that there is a host galaxy around the fast radio burst, a particular one. Turns out that this evaporated, this claim, especially thanks to Peter Williams and Ido Berger, that within a day or two showed that actually it is an AGN probably coming, producing that radio afterglow that was claimed to be associated as fast radio burst. And it was sort of clear from the start to Peter and Ido, because the radio luminosity was, if it was not an AGN, it was consistent with a star formation rate that was orders of magnitude above the limit from the H alpha emission from that galaxy. So it was clearly something else going on in that galaxy, the steady level of radio. And actually, in the paper that is not yet posted on the archive, they show that the variability could be due to scintillations of that AGN. So it's clearly not associated with the fast radio burst. But just a week later, Nature publishes a second paper on fast radio burst, which is inconsistent, obviously, with the paper last week, claiming that this one, Arecibo burst, another fast radio burst, repeated 10 times. Now, if it were cosmological at the redshift of order unity, then you would expect the origin of the fast radio burst to be a cataclysmic event, an explosion, a merger of two compact objects that would not repeat, just like gamma ray burst. But this particular Arecibo burst, the only one, or the first one I should say, that was detected other than by the Parkes telescope in Australia, when they looked at it a few years later, for a few weeks, they found it repeating twice, and then within the same day, actually within an hour, they found 8 repetitions, 6 of which were within 10 minutes. And that's what they report in this paper. There is a repeating fast radio burst. Now the question is, what does that tell us about the nature of fast radio burst? And even though there are only 16 or 17 known, there are already 3 classes. Type 1, Type 2, Type 3, because if this one, I mean, there might be a class that repeats, it cannot be a cataclysmic event, so it can't be associated with a gamma ray burst. So if you want to have a gamma ray burst, then it's Type 1. If you want to have a repeating burst, it's Type 2, and then there could be something also galactic. It basically shows that we don't really know what the origin is. They attribute fast radio bursts in the paper to magnetars, potentially very powerful giant bursts, flares that are much stronger than the ones we see in our galaxy. But if that's the case, if, for example, this source is coming from a galaxy at 100 megaparsec, because otherwise it would be really impossible to have a magnetar produce produce such burst, then the galaxy should be looming on the sky. It should be like an arc-minute in size, and we should have seen it. So it would be very interesting to search for optical counterparts of this particular FRB. And time will tell what the nature of FRBs is. I just wanted to mention that there is a repeating one 10 times, and the repetitions are clustered in time. It's not like, it doesn't look like there is a periodicity as if it was a pulsar, for example.
And by the way, I should just mention that I promised Scott Ransom, who's one of the authors here, that Peter and I will try to refute this in 24 hours. So far, we haven't been able to.
No, this one looks real.
Yeah.
Scott Ransom is a good guy. So is Richard Shappee.
The only inaccurate statement in the press release of this paper was that this is the first time a repetition is found, but in fact there were two FRBs in the past that overlapped in their arrow bars, in the arrow boxes on the sky, and they could have been associated, they could have been the same FRB. So it may not, and obviously this one was detected by Arecibo, but the repeating FRBs should be found by other telescopes as well. So stay tuned for the truth about the actual sources of FRBs. We'll see what they are. So today we will start with Reem Sari, that is visiting us at the Radcliffe Institute on sabbatical from the Hebrew University in Jerusalem. And he will talk about cooling, accretion, and retention of super-Earth's atmospheres. And he will be followed by Jim Stone, just gave the ITC Luncheon, and he will talk about global MHD modes of accretion disks in cataclysmic variables. And then we will hear from Karin Oberg, our own member of the ITC, and she will talk about isotopic tagging of volatiles during planet formation. And finally, we'll hear from Ben Shappee, who is somewhere, or yeah, over there, and giving the CFA colloquium later today. And he will talk about constraining type 1a supernovae through nebular phase observations. Reem will use a non-conventional method of presentation.
Best PowerPoint ever. So, yeah. So I'm very no, the lights on. I'm very happy to be here. I came here to hear all the news as fast as they are coming. And indeed, as I said, we have a new thing coming almost every week. Except the last one is not really a good example because I heard about it in a conference in Israel 2 months ago. So, okay. This talk will be somewhat influenced by the fact that a close buddy of mine passed away this past week. But it's not so sad because it should be easily replaceable at the Apple Store. But for now, that's the result of this effect. Yes. So I'm going to talk about super Earths. This is a good place to talk about it because many people here measure these objects. We're talking about objects which are a few, 1 to 10 Earth masses, maybe even slightly more, and they have some unusual atmospheres around them. So they have a significant fraction of atmosphere around them. How do we know that? So as you know, radial velocity of stars allow us to measure planets around them with very good measurement of the mass of the planet that is orbiting that star from the amplitude of the radial velocity. And transits allows a very good measurement of the size of the object. A combination of the size and the mass gives us a density. So just this simple fact that we have a density already can tell us in some cases that planets have big hydrogen atmospheres. If the density, for example, is less than 1, there's probably no other way to explain that but hydrogen atmosphere. So we think that cores of planets are probably rocky, maybe icy. That gives you within a factor of 2 the density. So it's maybe 2 to 5, like the Earth. And if you measure densities below unity, what that means is that some extra volume was given to this planet by something which has very little mass. So you can build your own model to understand how much mass is there. It's very easy. You just take density of hydrogen. If it's cold enough, it's about 0.1 gram per cubic centimeter. So, and you assume whatever your favorite core is, if it's icy or rocky. Since all these detected planets are on close orbits around the star, we'll assume that the core is rocky. So let's say the density of 5. So you combine a two density material from two densities, rocky and 0.1, to get the size that you want. That gives you an immediate estimate of the mass of the atmosphere, given the density that you have measured. So people have done that, and they get some planets with a wide range of atmospheres, from 5% to maybe 20, 40%. And my goal was trying to understand what controls that. Does it depend on the density of the nebula that the planet is located in? How it depends on the core mass? And is our theoretical assumptions or calculations compatible with those observations? So you should imagine the problem I'm trying to attack is the following. You take a planet or a core who has a mass of a few Earth masses. Let's say it's about this size. And you embed it in a disk. Now the disk, even the scale height of the disk, even though the disk are geometrically thin, is significantly bigger than the planet size, even significantly bigger than the gravitational reach of the planet. So the gravitational reach of the planet, you can either think of it as the Hill sphere, where the gravity of the planet is stronger than tides from the star, or the Bondi radius, when the gravity of the planet overtakes the thermal motion of the gas particles. But both around 0.1 AU away from the star are comparable, and are within the scale height of the disk. So the picture you should imagine is an infinite surrounding. This is the disk, but the edges are unimportant, and the fact that it's a disk is not so important. And you just put a planet inside it in a uniform surrounding. And then you ask yourself how much gas would be accreted. So the first thing comes to mind is Bondi accretion. And even when I was in grad school, Ramesh came to the Hebrew University and was telling us that you have Bondi accretion that's very good, and if you have a black hole inside, all the material will go to the black hole and there will be no signature of the surface. So we're exactly in the opposite limit. We have a surface, we're sure that these planets are not black holes. And the material that is coming is not limited by the Bondi rate, which is very fast, but it's limited by the fact that the material is hitting the planet and it's stuck there. So the first thing that happens on our free fall timescale, free fall at the Bondi radius, which is about a day, right? The free fall at the surface of the Earth is about an hour. The Bondi radius is about 10 times larger at 0.1 AU, so it's 10 to the 3/2, 30 times longer, so about a day. So in the free fall time, you get this Bondi accretion. If you just place the planet into a disk, a pre-existing core into the disk, and you form an atmosphere. But this atmosphere, if it just fell to the surface of the planet adiabatically, the surface density of it is so small that the overall mass of the atmosphere is about 0.1% of the mass of the planet. This is an unimportant atmosphere. So all this adiabatic thing is irrelevant. Now what we have is cooling of the atmosphere. So as this atmosphere cools, it accretes more and more gas, which condenses on the planet. And since the only way to transport heat outside in order to cool and to accrete more gas is by convection, you form an adiabatic atmosphere to the planet. So now let's get some intuition. So what do we expect the profile of these atmospheres to be? So you're all familiar with the isothermal atmospheres, like we have roughly on the Earth. So they have a scale height, and they decay exponentially over that scale height. If you have an adiabatic atmosphere, as you go up, the density is going down over the same scale height, but also the temperature is going down. So the scale height is becoming shorter and shorter. So actually, if you have, let's say this is the surface of the planet, this is height, and you're thinking of the density, instead of falling off exponentially over a scale height, it falls faster than exponentially because the scale height is becoming shorter and shorter. And depending on the adiabatic index of the gas, this is about 5 times what you naively would estimate as the scale height. Scale height would be kT over g mu. So at about 5h, you will get to 0 density. But these atmospheres of these planets cannot be like that because the Bondi radius is much bigger than that. It's about 10 to 20 times bigger than the size of the original core. So in order for this atmosphere to fill all the way up to here, you must have the temperature at the base high enough so that the scale height becomes comparable to the size of the planet. So what these atmospheres look like, they have a density profile which is just a power law all the way to the Bondi radius, with the temperature going like 1 over the radius. This follows directly from here if you put h equal r. So the temperature falls like 1 over the radius, and the density falls as some power law of the radius from a adiabatic relation between temperature and density. So we have power law atmospheres, and for gamma of around, let's say, 7/5, which is probably the right one for these atmospheres, you find just from these considerations that most of the mass in here is in here, and most of the energy of the atmosphere is in here. Okay? So now this atmosphere is cooling from here, it radiates out. More and more mass is cooling, is coming on. You have to lose this amount of energy in order for the atmosphere to gain more mass into it, but most of the mass is still residing farther out. Now this goes on for as long as the disk exists, and the growth rate of the atmosphere in this case is proportional to the time to the 1/2. The reason that it grows less than linearly with time is as time passes, there's more mass in here, the opacity in here is bigger, it takes longer time for the atmosphere to cool, and you need to cool farther because you have more energy to cool. That gives you this T to the 1/2, these 2 powers of the mass, one from here and one from the opacity. Okay, so what can happen next? There are 2 options. One, the amount of mass you accreted is large enough within the age of the disk. Let's say the age of the disk is 1 million years, 1 to 10 million years. Within that age, you can either accrete mass which is bigger than the mass of the planet, the original core that you put in. In that case, you have a runaway accretion, because now the gravity of the planet is changed. These considerations start to change because G is now affected by the mass of the planet. You have a runaway process, and you grow and you form a Jupiter. Wow. So, if I take temperature and the mass of the planet, I have an upper limit here that I can easily calculate from this consideration. Anything above that will turn into a Jupiter. Okay, there is another line that we can calculate, which is what is happening after the disk disappears. So now let's take this structure and get rid of the disk. What will happen is that the atmosphere will try to arrive to equilibrium with empty space. So it basically will start to evaporate. Evaporation will start here in something comparable to the Bondi rate, which is, we already said, is very short. So that happens very quickly. But it's energy limited. You need someone to supply the energy for the evaporation. But since most of the energy is here, all this atmosphere that you are accreted far away from the planet. So if this planet is this size, this is the Bondi radius, much larger than it. But it has no energy. The binding energy of this is small. So it can all be evaporated, taking the energy from here. So the evolution of the system is like that. It gets truncated. And the cool thing is that the time scale is very easy to understand, because it's the same process that formed the atmosphere that also gets it evaporated, just the thermal energy that it has. And therefore, I can show that the atmosphere disappears from the Bondi radius all the way to twice the radius of the planet in the same time scale that the disk accreted it. So in an extra million years after the disk disappeared, you lose all the mass of the atmosphere, and you remain with something like this. Now what happens next depends. There are 2 options. One, for light atmospheres, they will continue to evaporate because they will remain hot by the core itself that you put in here. For heavy enough atmospheres, they have actually bigger heat capacity than the core. Now how that can be if the atmosphere is small in mass, because the atmosphere is made out of hydrogen, while the core is made out of particles which are 20 times heavier or something like that. So it's enough to have 5% in mass in the atmosphere that most of the heat capacity will be that of the atmosphere. That gives us another line in here. that says that any atmosphere lighter than that, so any planet which is low enough mass, therefore it accreted in this stage, low enough atmosphere, will completely evaporate, and we expect no atmosphere in here. So nothing in here, nothing in here, and I'm out of time, but we can also put a UV evaporation timescale, and we remain with this single area where you can have planets in this diagram. So if you give me T effective, which is basically the distance from the star, and the mass of the planet you observe, we basically are saying that there will be, all the objects would be in here. And this seems to be pretty much compatible with the dozens of observations we have. Thank you. This is somewhat, no, this is more massive, and also this atmosphere is hydrogen atmosphere. I don't know if you want to breathe it. So it's not yet with the habitability, but this is like 500 degrees is here. This is like a few thousand degrees, maybe 1500. So this is hot. Yeah, habitable zone is there.
Within the snow line or beyond the snow line, whether there's any substantial difference.
Okay, so
a lot of volatiles would be delivered by ices.
So it just, okay, the other elements can be important for two things. One, for the mean molecular mass of the atmosphere, which is important. So I heavily use the fact that it's hydrogen in here. If it's mostly water, this is something else, okay? And the other thing is that the opacity may be affected by other molecules, but I'm not sure that is that important in the range of temperatures which are high enough. So my guess is as long as you're in the range of around 0.1 AU, if the mean molecular weight is not that different from hydrogen, I think it's not going to be vastly different. Far away, it's a different story.
So you gave this completely spherical picture.
Absolutely.
But this disk has got angular vorticity, and so there must be some angular momentum constraints. Is that important here?
I think not. So as long as the Hill radius or the Bondi radius, which gives this upper limit, is much smaller than the thickness of the disk, I think there are not going to be huge effects. People are talking about that it does something, but I think it's not huge.
It's a question of whether the gas can hit the surface directly or will circularize outside this core.
There is no heat in the surface directly. You have to cool down. So you think of these atmospheres arriving all the way to the Bondi radius. So there's nothing to fall, right? The disk is here and the planet is here. They're touching. There's no big gap. You're thinking of an empty Bondi sphere that collects stuff from the surrounding. That's not the case in here. The Bondi sphere is full with gas that is much denser than the surrounding. That's a different picture than the black hole case. Right? In the black hole case, the density is uniform in the surrounding and falls. Well, actually, it also goes up. Yeah, but here there will be a bigger jump of the density.
Thank you very much, Randy. You can move
I'm nervous now after Rem's computer died that this one's going to die. Let's just make it through this. Where's that? Lights. Okay, well, this morning I spoke about work that had been done by postdocs and students at Princeton, Zhao Zhu, Jinbai, Rubing Dong. Today I also wanted to talk about another project from a Princeton student who's doing a thesis work with me, Wenha Zhu, on cataclysmic variable stars. So back in the old days, 80s, 90s, these were very, very important and well-observed top stars. I get the sense that not many people work in them so much anymore, so maybe I need to explain a little bit of background. So cosmic variable stars are binary systems in which there is a a white dwarf in a close binary with a secondary. The secondary is usually low mass, which is is evolving off the main sequence, beginning to expand and fill its Roche lobe, and so then there is mass transfer from the secondary onto the onto the white dwarf. These systems are typically separated by less than 1 solar radius, so these are very, very tight binaries, and so the mass accretion results in a accretion disk and a boundary layer, and these are then very, very bright sources because of the accretion powered emission from the disk. So why would we be interested in CVs? Because there's so much observational data taken on CVs. Now, as their name implies, they're variable. There's a subclass of CV disks or CVs called dwarf novae, which undergo periodic episodic outbursts. Here's an example, V1504, which happened to lie in the Kepler field of view, so there's outstanding photometry on this system. And you can see these beautiful regular outbursts as the disk brightens up, typically over a few hundred orbital periods of the binary system. So this has been modeled over the last 20 or 30 years as a classical thermal instability model in the disk, where the angular momentum transport rate, described by a Shakir-Tsarnaev alpha parameter, has sort of 2 states. There's a cold quiescent state where alpha is small, and a hot outburst state where alpha is large, and the change in the angular momentum transport and therefore mass accretion rates explains why you get the different luminosities during the 2 phases. The point here is that there's actual direct measurement, or as direct as we can get, of what the transport rates are, what alpha is in the disk. There's very, very few accretion disks where we can actually make measurements of alpha. By modeling the shapes of these outbursts, we get direct constraints. So this is very important if we're interested in constraining the theory of angular momentum transport in these disks. Moreover, because many of these systems are eclipsing, you can follow the time evolution of the light curve during eclipses, and you can match, or you can model the radial profile of the accretion disk as it's slowly eclipsed by the secondary star. Moreover, because you can use Doppler information about the line of sight velocity in the accretion disk, you can actually map kinematically the emission and structure of the accretion disk. And so we actually get images and measurements of the size of the disk. We know the disk, for example, is typically a half the size of the Roche lobe in quiescence, and at outbursts it actually grows in size, almost to the size of the Roche lobe. Moreover, from this so-called technique of Doppler tomography, we can make images of the disk. This is really amazing. These are systems we're never going to resolve spatially with our telescopes, and yet we can make, from inferring the Doppler structure, inferring the kinematics, we can make images. And so during outbursts, we often see these sort of spiral structures in the disk. So there's a tremendous amount of data here that we should be able to use to constrain the theory. So Wendy's thesis was to revisit these systems. Back again in the 80s and 90s, 2000s, there was a lot of work done modeling mass transfer and accretion and hydrodynamics using these systems with an alpha viscosity. Our goal is to come back and do this again using MHD simulations to model the MRI, which is now thought to be the mechanism for angular momentum transport in these disks, and see whether or not anything changes if you directly model these systems with MHD. So our idea is to take a computational volume that encompasses the entire accretion disk. We don't follow the secondary star, we just inject material at the Roche lobe, allow it to fall into the accretion disk and build up a disk. And then we're going to model how the MRI grows and saturates in this system. So typically we're using mass ratios 0.3 or so. We're in a frame of reference co-rotating with the white dwarf, so the white dwarf is centered on the mesh at all times. We inject magnetic field in the accretion stream. We just have little field loops that are being advected inwards with the accretion stream. We don't really know what the magnetic field geometry is in the accretion stream, so we're just making an assumption here. And then we're using cylinder coordinates and so on. Maybe it's best to understand what's going on by watching a little movie. So here's an animation as we inject plasma from the Roche lobe into the system. It falls in ballistically, but then shocks as it hits itself. It circularizes. Eventually, an accretion disk builds up here. So this is the density. This is the magnetic field. And you can see the growth of turbulent, highly unstructured magnetic fields here. The MRI has become active. It's producing angular momentum transport via turbulence. And this a great movie, it goes and goes and goes and goes. So another important point is that the timescales involved here are relatively short. They're reachable by computational methods today. We can easily integrate this for hundreds of binary orbital periods. That's mostly because the dynamic range between the surface of the white dwarf and the Roche lobe is only about a factor of 100 or so. That's well within reach of computational techniques. So we can do simulations that span an interesting amount of time to model the data directly. So one thing that comes out of right away is you begin to see these spiral structures in the disk that just don't go away. They're always present. It's not homogeneous turbulence. There's this background spiral structure in the disk. And of course, that's being generated by the non-axisymmetric torques due to the secondary star. There's a gravitational torque on the system which is producing this density wave. And what was surprising to us is that the angular momentum transport due to those spiral waves measured by some kind of Reynolds stress, this black line, actually was larger than the Maxwell stress. And I've grown to the point where I think MRI is really important. It probably dominates angular momentum transport in most circumstances. But here's an example where a purely hydrodynamical process, namely these density waves, was dominating the MRI, but only in certain cases. This is a case where the gas is pretty hot. The Mach number in the disk is only 5 to 10. And then you have a very strong spiral pattern. If you make the gas a lot colder, the Mach numbers are 20 or so, then it's back to having Maxwell stress exceeding Reynolds stress. So there's a profile of stress versus radius. The black line is the Reynolds stress. The dotted line is the Maxwell stress. So clearly, sometimes spiral arms are important and sometimes they're not. And so we wanted to understand that a bit better. So Wendy did a whole series of calculations. She even went back to doing hydrodynamical calculations to understand the excitation, the propagation, and damping of these waves in these CV disks. And so one thing that we found is that the simplest model you can take, namely just linear theory, works extremely well in describing the properties of these spiral modes. Namely, so these plots show you the surface density, but we've unwrapped it into a Cartesian coordinate system, so radius and phi instead of a cylindrical coordinate system. And you can clearly see these spiral density waves. And then we've measured the pitch angle of the spiral wave just by every little black line is a point where the pitch angle of the spiral wave was measured. We plot that pitch angle versus 1 upon this quantity here, which depends on the sound speed. And the dashed line is the prediction for what this pitch angle should be as a function of this variable, basically sound speed. And you can see that the measured pitch angles fit the linear theory extremely well. That is, the shape of these spiral arms basically is just linear theory, that these waves are not strongly nonlinear, they're only slightly nonlinear, and so they agree with the linear theory for these density waves extremely well. So that explains the shape. It's important because there was a lot of work on self-similar models for spiral arm or spiral shock waves in these disks. That doesn't work very well at all. It's just much simpler than that. It's just basically slightly nonlinear waves. So armed with that, Wendy's just finished a paper which is now submitted, and I'll just summarize in my last slide here what are the major results. So first of all, the excitation of the waves is a very complicated process because the excitation is occurring at Lindblad resonances, which are outside the edge of the disk. In most circumstances, therefore, what matters is the size of the disk. If you make the disk larger, there's a larger overlap with the resonances. You get much stronger excitations of waves. You get much stronger spiral waves. We can't control how big the disk is. It's as big as it wants to be. The dynamic self-consistently controls the size of the disk. So excitation of the waves is highly coupled to the internal dynamics. In fact, this is where MHD makes it really interesting because angular momentum transport by MRI turbulence makes the disk grow. It makes the outer edge of the disk expand because mass has to move outwards to absorb the angular momentum being transported outwards by the MRI. That then increases the coupling to the resonances and drives stronger waves and makes hydrodynamical processes. So there's this very complicated feedback mechanism between excitation and other internal dynamics of the disk that is going to take a while to sort out in real systems. So second major finding, as I've already mentioned, is that the shape and pitch angle of these disks is well fit by linear theory. The m equals 2 dispersion relation works extremely well. Major finding 3 was that we've been able to, because we're doing this computationally, we can measure the size of every term in the angular momentum equation. We've been able to show explicitly that the mass accretion rate driven by these spiral waves is exactly equal to the dissipation, or exactly equal to the amount produced by dissipation of the waves. So that is to say, the transport by these waves is not like an alpha viscosity. It's not a local phenomena. You're exciting the wave at the outer edge of the disk. It propagates carrying negative angular momentum, and there's only transport when the wave damps, because when the wave damps, it deposits the negative angular momentum into the disk, and then that represents a net transport of angular momentum. Without dissipation of the wave, there is no net transport. And so we've been able to show that the waves shock and dissipate in the internal region of the disk, and we've been able to show explicitly that the mass accretion rate in the simulation is exactly equal to the amount produced by the dissipation of these waves. So I think that's the first time we've been able to do this so carefully. And then finally, we've been able to show that the effective Shakura-Shinyaev alpha parameter is a few hundredths. It's sort of consistent with the values you get in the quiescent state. So there is a model for the outbursts where quiescent state, the disk is cold, it's not very well ionized, there's no MRI, and the accretion is strictly driven by these spiral waves. Alphas would be around 0.01 in that case. That's at least consistent with the values we measure. In the hot outburst state, then you also have MRI contributing to transport, and you might have a larger alpha. So that seems to sound like a nice picture. The only problem is that in the cold state, the Mach number is extremely high, and if you remember the images I showed you before, the spiral waves are very weak when very, very high Mach numbers. So there's a little bit of an issue that at the realistic Mach numbers in the cold state, there may not be very much spiral wave amplitude. And with that, I will finish.
So Jim, you were mentioning the tidal interaction as
Yes.
one of the things that's driving the spiral structure.
Right.
But there's also the stream
Yes.
coming and hitting, and
Right.
it's also in phase
Yes.
with the spiral
Right.
arms. I was wondering how much role it plays.
So
Hitting one point on the disk.
right. They both contribute to exciting waves. So we did calculations in which you just start with a disk out to some radius and don't have a stream at all. Then you know the spiral wave is induced entirely by the torques from the secondary. The shape of the wave, the transport properties, and so on agree entirely in that circumstance. So the gas dynamics doesn't care so much how the wave is being excited, it seems. So that is when you put the accretion stream in, now you also have the torques, the gravitational torques, as well as the impact of the stream. It didn't make a didn't make a qualitative difference. It makes a quantitative difference in the exact accretion rate you get and the profiles of alpha.
You know that in cosmology, when galaxies merge, it's often talked about that gas is funneled to the center of the merger.
Mm-hmm.
Part of it is the loss of angular momentum due to the spiral arms being driven by the perturbator.
Mm-hmm.
Physics might be quite similar.
Right.
In principle,
Right.
apply to those.
Right. Probably in that case, self-gravity also is contributing in the galactic case. Here we're not including self-gravity in the disk at all. It's just the potential of the white dwarf and the secondary star.
Yes. Density wave can be excited at dim resonances, but they can also be excited at sharp edges. They have to be sharp compared to the wavelength of the wave, and it seems to be that this is the case here. So it just may be an excitation at the edge rather than the resonance.
That's true. I mean, that might contribute. I mean, the one thing that suggests resonances is that if we make, if the disk gets larger, you do see a much stronger amplitude in the wave. So that's sort of consistent with getting closer to the resonances. It's very difficult to do a very carefully controlled experiment to investigate this sort of things because we don't get to choose what the shape of the disk is or what its edge is. It's determined entirely self-consistently with the dynamics. It is what it is. And so it's hard to sort of separate one effect from another.
You can take your simulation and theoretically calculate the driving and see if it comes.
Yes, we tried to do that, but at least for the excitation of the driving is exponentially sensitive to where you determine the edge of the disk, and that, there's no edge. There's just some power law at the end where the density falls off. So that's actually very difficult to do that calculation.
Thank you very much.
Yep.
Well, it seems like the unifying theme so far is disks, but I guess we'll switch back to more of the protoplanetary disks with this talk. And particularly what I want to share with you are some progress that we're making in understanding how we can trace the origins of volatiles in the solar system. By understanding better the origin of these kind of patterns, chemical patterns that we see in protoplanetary disks. So there are two related problems that we're trying to address with this study. One is that we know planets form in disks, and the planet compositions should depend on where in the disk the planet forms. So if we understand the chemistry of the disk well enough, we should be able to trace back the formation location of planets based on their compositions. The second question is that we know we have one planet here that has sufficient amount of water and organics on it to have led to the origins of life, and that how important in the early days of the Earth delivery of volatiles was, so how important this picture really is, versus that the Earth formed with sufficient amount of water and organics. So those are two questions we want to understand. And you can think about that in the previous slide I showed, when we were thinking about the overall compositions of planets and using that to backtrace the formation location, you have quite a few different options available to you. Maybe you can look at the elemental composition or the molecular composition of those different bodies. And if you understand the chemistry well enough, trace back to where they formed. But if we want to answer this question here, that is how much of the Earth's water that came from comets and meteorites instead of forming with the Earth, we really need something that's marking water itself. We really need a tag on the water itself that tells us where it came from. Luckily, we do have such a tag available to us, we think, which is the abundance of heavy water compared to normal water. And the reason we think this has great potential as a tag is that you only move deuterium into molecules under very specific conditions. So this here shows in a simplified form the chemistry of isotopic enhancement in molecules. So what's going on is that the main reservoir of deuterium during star and planet formation is HD. So what you need to do is move that deuterium from HD into your volatile that you're interested in. And this happens in very cold environments because of small differences in the 0-point energy between the normal molecule and the heavy molecule. That is, you can think about the molecule just as two atoms attached to a spring, and all else being equal, if you make the two masses that are attached to a spring heavier, you lower the energy of that system. So this means that you will go from having H3 plus to H2D plus. That would be an energetically favorable reaction to have. But the energy difference between those two molecules is very small. So this is only going to be important when you're sitting at very low temperatures. Think about 20 Kelvin or so. Once you have H2D plus enhanced, you can move that deuterium into a range of other molecules, such as DCO plus, that's just attaching that deuteron to CO. Or you can combine it with an electron to form a deuterium atom, which can react with OH on grains to form deuterated or heavy water. So that's, if this is the only pathway to enhance the deuterium level in molecules, then what we should see is that the colder environment you go to, the more deuterated molecules you have, and the origin of the Earth's seawater would actually be quite trivial to determine, because we have such an enhancement on Earth by about an order of magnitude, which should then mean that the Earth's water came from a very cold place. The problem is that this is not the only way that you can add deuterium to molecules. There are also warmer pathways which really work in a very similar way. You move the deuterium from HD into another ion or molecule. But there are pathways that don't require as low temperatures as the H2D plus pathway, simply because the energy difference between the heavy and normal ion is much bigger. So this pathway here could be active up to 50, 60, or 70 Kelvin, which is more the inner solar nebula rather than the outer cold comet-forming one. So that's the bad news. the good news is that in theory we should be able, with observations, to determine which one of these two pathways that is the most important during planet formation. So this is a cartoon of a protoplanetary disk, and the only thing that's important for this talk is that you have a temperature gradient in the disk going away from the star. And if we resolve where we have deuterium enhancement in these disks, we should be able to tell whether we get high DTH ratios all over the disk, which would tell us that both these warm and cold pathways are important, or whether we just get it in the outer disk where only the cold pathways would be active, or whether it's species dependent. It might be that for some molecules we see something across the disk, or for some molecules they're only enhanced in DTH in the outer disk. Now, our very early studies of this, which we did with SMA and with ALMA at a very, very early stage, seemed to tell us something that made actually perfect sense with the models, which is that for DCO+, which is a molecule that we think can only be deuterated like water through this very cold pathway, we see that we have a central, this is low signal to noise, but we have a central hole, and then we have what looks like a ring at larger radii in this particular disk. And this makes perfect sense. You'd expect low DCO+ towards the warm center, and then a gradual enhancement as you go outwards. And then for this other molecule, DCN, we see something that's centrally peaked, which actually also confirms models, because DCN is one of the molecules that could be deuterated through this warm pathway as well. So that was good news, and then we made the fatal mistake of trying to enhance our sample from 1 to 7 sources using high resolution studies with ALMA. And what we get is this. So on the left column is just the continuum, so that just shows the dust disk. And then we have HCO+, so that's the normal version of DCO+, and then HCN and DCN. And what I want to focus on is just DCO+, so the molecule that we think we understand the best how it's deuterated. And what you see is that we see a range of structures in this disk sample, which is rather distressing if you want to be able to tell that we understand this molecule's chemistry well, and these should all be similar objects. So the question now is the chemistry just too complicated to use this DTH ratio, or is it actually physics that is the complicating culprit in this case? So what we did do was to start with the most complicated structure first, which is the second one from the top, which is actually a double ring in DCO+. So zooming in on it, this is what it looks like. So what you see is, so it just shows the overall integrated emission in DCO+, and then here it just shows that it is a rotating disk in DCO+. So I think what's first important to establish is what makes sense with this observation, what we expected. We expected the inner hole. I mean, this is where it's too warm for H2D+ to form. We also expected to see an outer edge to the DCO+ emission, simply because at some point it gets so cold that CO starts freezing out, and you need CO to form DCO+. What we did not expect was this second ring out here, but one of the clues to what might be going on is that this second ring actually coincides to where the millimeter grains disappear in this disk. So what we think is going on is that the chemistry probably is exactly what we think it is, but we have just a much more complicated physical structure in these disks than we had expected. So what's shown here is a cartoon of a disk. And what's shown in blue is the region where CO is frozen out. So you have an inner radius where C is frozen out because it just gets too warm and CO sublimates. But then at some point you will hit the radius where UV, either from the star or from the interstellar medium, can penetrate into the disk and non-thermally desorb some of the CO back into the gas phase. And where it would make sense that we would see that is where the dust disk gets so tenuous that it starts disappearing. So we think that is what's going on in this disk. And when we do more, not just the cartoon, but more quantitative modeling, which Ilse Klees is doing right now, this picture seems to be confirmed. I should mention, though, that there is another theory, what might be going on out here, another way to return the CO to the gas phase, and this is also Ilse Klees' work, is that you might have an actual thermal inversion happening right where the millimeter dust has disappeared because of drift of this millimeter dust inwards. But in either case, we think the chemistry is working, and the chemistry is actually simple. And the reason we see these complicated pictures is that these disks, when we look at them at higher spatial resolution, turn out to have much more complicated dust structure than we had seen previously. So the conclusions are that we still think that these isotopic ratios or isotopolog ratios are very powerful messengers, that they tell us something about where the volatiles originated from, both in our own solar system and, of course, in other disks where planets are forming right now. And the really good news is that we're going to be able to continue to test these theories, not just with DCO+, but with other molecules as well. And though our first survey reveals this range of patterns, at least our first case study seems to suggest that for once, it's not the chemistry that's complicated, but the physics, which is, very, very comforting. And with that, thank you for your attention and any questions.
Do you have any information about the ages of the systems, or could that have anything to do with the different patterns that we see?
So the exact ages are uncertain. So 5 out of 6 of these disks we think are on the order of 1 to a few million years old. And then there's one of the disks, not IM loop, not this really strange one, but one of the other ones, which is probably closer to 10 million years, which is the oddball. But most of them are on the order of a few million years.
The DCO plus, Karin, can be destroyed with a recombination with an electron. If the dust is changing in size and the UV is penetrating farther, might part of this explanation lie in an increase in the fractional electron abundance, which is then free to combine with the DCO plus?
Well, but then I would expect to see, at least I would think that the ionization degrees, so the electron density, would be the highest, either very close to a star or out here in the tenuous medium. So that wouldn't really explain why you see the reappearance of DCO+. Maybe it explains why you see it disappear a second time around. That could also just be our sensitivity. But that will lead to the destruction of DCO+, not the reappearance of it.
Is it very clear that the current overabundance of deuterium on Earth is the primordial one, or could it have lost its hydrogen through the upper atmosphere preferentially rather than deuterium?
So my understanding is that for Earth, that should not have been very important. Like, you should not have been able to get to the order of magnitude increase in the seawater. While on Mars, for example, it is probably the explanation.
Karin, just a comment. It's a very powerful combination to have you as an observer collaborate with Ilse, the theorist at the ITC corridor, and we see that in play here. And we hope that this will continue for many years.
So do I. Thank you.
Oh, the other plug was his?
Yeah, it's so there are
What does it mean?
an adapter. No, he has one.
Do I need HDMI or? The new one, of course, they keep changing it. There, this is perfect. So I hate to break the trend that we've already had of disks in every talk. Today I'm going to tell you about constraining type 1a supernovae through observations of later time observations, especially in their nebular phase. And of course, we all know that 1As are extremely important for cosmology. Their use as a tool was awarded the Nobel Prize to discover the accelerating universe. But it's still a point of embarrassment that we still don't know what the actual progenitors of these objects are. And so the basic distinction that you would like to make is that is between these two general classes of models are type 1a supernovae due to the merger of two white dwarfs, two carbon-oxygen white dwarfs. They can merge through gravitational radiation. You can help gravitational radiation if you add a third body. You basically pump the eccentricity of the inner binary. This causes gravitational radiation to be more efficient, significantly more efficient, so you can merge wider space binaries. Or perhaps if you set up a triple system just right, you can actually have eccentric cosi. You can actually have two white dwarfs collide head-on and explode. But these are all the double degenerate class of models. On the other major class of models that you'd like to distinguish between for type 1a supernovae are the single degenerate class of models. And here you have a white dwarf. I guess I do have a disk, actually, right there. You have a white dwarf that's accreting material from a nearby companion. You build up the mass of the white dwarf to the point where you're near the chandrasekhar mass. And eventually you explode the white dwarf this way. There are many different small tweaks to this model in the single degenerate scenario, but that's the main picture that you have, is that you have a white dwarf that's near the chandrasekhar mass and explodes, and it has a nearby non-degenerate companion. There's three main observational signatures that can possibly distinguish between these two in late-time observations. And they're basically due to a difference in burning conditions, interaction with the companion in the single degenerate scenario, and symmetry or bimodality of the nebular phase spectra. I won't talk about the last one because I don't have time, but if you're interested in this one, it's basically due to, in the double degenerate scenario, if you collide two white dwarfs together, it's a non-symmetric system, and you couldn't possibly see this in late times. But if you're interested in this, see Subodong's paper. So I'll talk about the first two. So with burning, density is your destiny. So there's a fundamental difference between these two models. So in the single degenerate scenario, you have a white dwarf that's near the chandrasekhar mass. So the core is extremely dense where you're going to have your burning take place. Whereas when you have two sub-chandrasekhar mass that you bring together, the burning occurs in a much different region. Both of these models, obviously, we wouldn't be discussing them if they couldn't explain the peaks of type 1a supernovae. So both of these models are constrained by observations already to basically fit the amount of nickel 56 that you produce. And this is exactly what powers the early time light curve. And they roughly produce the mass distribution. And with these two things, you can produce a reasonably looking light curve that can explain type 1a supernovae. So the models aren't free to produce different amounts of nickel 56 to explain single objects. But what they do is they produce different amounts of cobalt 57 and cobalt 55. And cobalt 55 immediately decays to iron 55 in a very short time scale, so you never see that. But what's interesting about these two isotopes is that their half-lives are quite long. And so they actually start to influence the very late-time light curves of 1As after 1,000 days. The problem with this is that type 1a supernovae are very faint at these times. So before a nearby supernova 11Fe went off, the latest time observations were around 800 days, and they were very low signal noise, so it's hard to observe a supernova this late.
How much cobalt they produce?
How much cobalt 57? I don't have the number off the top of my head, but I would guess it's less than a tenth of a solar mass. These are a very late time, so you're quite faint at this time. It's a good question, though. And so 2011 Fe was basically a golden standard. It was basically a gift to this field. And that's because it went off in a very nearby galaxy, just 6.4 megaparsecs away in M101. It was very far on the outskirts. There wasn't any extinction. M101's face on, which helps. It was also in a very low density region, so you can actually study this object at very late times. So what I show you here is some preliminary work that I've been leading. This is the light curve of 11 Fe. The very early time data is just what's published in the literature. The mid-time data, going from basically 300 days out to almost 1,000 days. This is all data from LBT that I've taken. And the very end is actually HST data that I've been, multiband HST observations that I've been given in the past 2 cycles. And I have one more observation coming up in this cycle. And what you can see is that we've now tracked 11 FE over a factor of 1 million in flux. These dashed lines were the previous latest observations of supernovae, of type 1a supernovae, before 11 FE went off. And you can see that we're finally getting to the point where we can distinguish between these two models. I wish I had final conclusions for you, but the problem is actually right now it looks like the IR might be dominating the bolometric light curve, but it's not clear how much of this flux is actually from 11 FE at this location. There happens to be a star nearby that's very red, and so we have to wait till later times to basically see if this continues to fade or if it basically plateaus to the luminosity of the star. But once we know this, then you can compute the bolometric light curves. And the nice thing about this is that you're making a differential measurement. You're not making an absolute measurement. So if you told me I had to have the bolometric light curve to a couple percent and an absolute scale at these late times, I would say you're crazy because we don't know the contribution in the far IR. But we're just making a differential measurement between about 1,000 days and then about 14 to 1,600 days later. So you can see that these, if you constrain the point here, there's actually a substantial difference between these 2 models in the bolometric light curve. So we'll be able to distinguish between these 2 models with these observations. Another interesting thing is that if you have a supernova and you have a single degenerate supernova, then the ejecta from the companion, from the explosion is actually going to strike the companion and interact with it. That's going to create a shock, which can give you early time emission, which I'll mention in my talk later today. But it also does other things. It sends a shock into the companion, which injects energy into the companion, and also removes material primarily through ablation. So you overheat the companion, and then the outer layers basically strip off. You strip off about 1/10 of a solar mass of material. But you don't really lose mass by momentum transfer. And this will be important in my next slide because the amount of material that you remove from a companion is actually intimately linked to the amount of energy that it receives. And this means that these are not uncorrelated parameters. So this is a hydrodynamic simulation of the interaction with the companion. And you can see that you're left with this very hot envelope. So the ejecta hits the companion, you go through time, and then at the end, after the ejecta has already passed, you're left with this big puffy object that's overheated. The velocity distribution of this material is around 1,000 kilometers per second. And this is important because the ejecta itself is at about 10,000 kilometers per second. So if you're looking for this material, you want to see if this material is actually there, you have to wait till late times because at early times, all you're seeing is the outer layers of your supernova ejecta, which are at much larger scale. So you have to wait for the supernova ejecta to become optically thin so you can look through it and see the inner regions. And this is exactly what I did for 11 FE. At a spectrum that I took at about 260 days after maximum light, you basically look for H alpha emission. It's very simple. So then you look for H alpha emission that has a characteristic velocity of about 1,000 kilometers per second. This is the spectrum right here, shown in black. The underlying supernova continuum is the observation is the black line. The mid panel is just a telluric model, so you can see that this line isn't real. It's just a telluric feature. And then the game you play is that you just smooth the supernova spectrum at a size scale much larger than 1,000 kilometers per second. You then subtract that off, and you just look at your residuals, and you look to see if there's any hydrogen there. In this particular spectrum, this dashed red line, this is by far the deepest limit placed on hydrogen for late time 1A. This is 1,000th of a solar mass of material converted to flux. So this is about 100 times deeper than the expectation from hydrodynamic simulations. So you can say for certain there is no hydrogen emission in the supernova. So maybe it's a double degenerate companion, or it could be a helium donating star. Another thing that's interesting is that the shock heating of the companion and the removing of material, if you actually evolve this star forward in time afterwards, you actually end up seeing that it's more luminous. So for the first 10 years, it's a couple hundred times the solar luminosity. So this is a model that I ran using one solar mass star. You strip off about 1/10 of a solar mass of material. leaving the star overheated, and then you just follow with MESA models the evolution forward in time. And what you can see is that you're significantly more luminous than the progenitor star was. So then you can look at supernova remnants. This is a particular one in LMC. And you say, oh, is there a bright, relatively bright star near the center of the remnant? You see nothing for this particular case, which is especially strong considering you expect the star to be very luminous. And finally, I'll finish, since I'm running out of time, going back to this plot, is that this is another thing that very late time photometric observations of supernovae can give you, is that you can look for this shock-heated companion at later times. And that's actually the model I showed you that I ran 2 slides ago is actually these dotted lines. And so you can see in next cycle of HST, we'll actually be starting to really constrain to see if you see evidence for this companion being there. So then we'll have multiple different ways to constrain the progenitors of type 1a supernovae, which is nice because you don't want to really rely on just one method for such an important constraint. Thank you.
So some of the double degenerate models with the helium donor star, you can get helium flashes prior to the main supernova event, and those flashes can inject mass into the environment, something like hours to minutes prior to the supernova going off at a similar velocity. I'm just wondering if there's any constraints on, say, the late time light curves of any sort of CSM interaction for 2011 FE.
There are interactions, there are constraints, but if you're ejecting it just hours before the explosion, that you would run into that material much earlier. So you wouldn't have to look at late time observations.
It's at a similar velocity, so in principle, they don't catch up to one another until later.
Oh, I see what you're saying. There is no evidence in the late time light curve. So there is evidence that it's flattening out, as you can see here. But there's no sharp features which I would contribute more to an interaction. But if the velocity difference is small, maybe you smooth out such a sharp feature. So I haven't thought about that much more than that, but that could be interesting.
We reached our time limit, and we order forward your talk later today. That's it for lunch.
Thank you. Well, the error bar, well, I should.
Just take off.
Yeah, I was just saying, like, we do the same program for 1BCs, your symbols, they're not criticizing the precision you're getting.
No, absolutely not. So it's much, much